Well, good morning, everyone. The first talk this morning is by Mihai Păun from Bayreuth, who will talk about solving the dbar equation on non-compact domains. Mihai?
Well, thank you very much for the invitation. I'm grateful. It's a great honor to give a lecture in this very beautiful event, and I'm really sorry not be able to join you live. Now, as you see, I will report on a joint work in progress with the drawer Varolin, and given that it's Friday morning for you and Friday afternoon for me, I try to make it as well friendly as possible. Let's see if I succeed more or less. Now, the plan for what you will see is as follows. After a short introduction and stating the main results, I would like to present a few techniques which are in the proof, and then some more general versions of the main result. So now let's start with the introduction. X will denote, as usual, one of the following objects. It's either a projective manifold, and then here most of the time compact Kähler manifold would be enough. And then another possibility, which is basically indispensable in this story, is the following. So we have a complex manifold M endowed with a metric G. And then we have also a smooth extension function defined on M. So such that this, these objects have the following properties. So G is a Kähler metric, right? And then the Hessian of psi of our exhaustion dominates a small multiple of the metric, right? So this is, of course, very familiar to you in both of these settings in algebraic geometry. Projective manifold is a projective manifold and can be, for example, the complement of an ample for hyperplane section projective manifold. And in this context, we take X to be the domain psi smaller than 1. This is a sublevel set. And then we make the extra assumption that the boundary is smooth. Okay, that is to say, the gradient of psi doesn't vanish at any of those points when psi equals to 1. Fine. Another piece of data is a proper analytic subset inside X. And then let's say that X0 is the complement. Okay. And then now let's consider also a holomorphic vector bundle on this open part, right? So you have your manifold X, and then you remove some bed or some analytic loci Xi, and then we have a holomorphic vector bundle on the complement of arbitrary rank. And then let's take a metric also on this bundle. For which the chain curvature tensor will be denoted like this, I theta of EHE. Of course, we always fix metrics because if there is no metric, then there is no geometry, right? Now, the motivation for what you'll see is the result proved by Bando some time ago, stating the following. So we have this very simple setting. X0 is simply the pointed ball in C2. And then, so assume that this metric here is smooth on the pointed ball, but then it's also that it's square integrable, right? So here you need two objects to measure this tensor, right? So the metric HE itself and the flat metric on the C2. And then the conclusion is rather strong that E is the restriction of a vector bundle defined on the whole ball. Okay, so from this curvature assumption, he derives that the vector bundle extends. And then the proof is really very interesting. So basically, that's what I want to talk to you today, the proof of Bando. And then, so what he does actually, in a nutshell, is it shows that the vector bundle E can be embedded in the trivial bundle of the pointed ball, simply by constructing holomorphic sections. And then this is exactly somehow the main theme of my talk. how to somehow accommodate this the construction of holomorphic sections under this assumption that the curvature is in LP for some exponents P. Wonderful. Now, what I would like to talk about, let's say, is the following. Let's assume that the dimension is at least 3, because in dimension 2 we know everything already. And then the theorem I would like to present is the following. So we take an analytic subset inside the X is as before, right? Codimension, unfortunately, at least 3. And then let's assume that the curvature, instead of being L2 in C2, is Ln in dimension n. And then there exists an ample in the projective setting, or simply E in the other one I was mentioning, such that for any 0-1 form with values in this bundle, so if you twist E with a sufficiently positive line bundle, then for any 0-1 form with support in this open part, and which is dbar closed, then the conclusion is rather, it's very interesting in the sense that you can solve the dbar equation and you have some estimates, okay? So the situation here is that, let me make some comments about it. Oh, yeah. So as a consequence of this result, as you might know, this is the kind of estimates which precisely allow us to construct holomorphic sections, which moreover are L2 integrable over this open subset. And then, what is the main difficulty in this story? Well, the main difficulty is that the curvature tensor, we only know that it satisfies some integrability assumption. It doesn't have any upper bound or uniform upper bound or lower bound. So that hoping that you take an ample which is big enough, then it will overpower the negativity that you have, because you don't know what's there, right? So that's the main difficulty in the story. And then let me mention also some other results in this direction. For example, very nice work by Cornalba and Griffiths, where they were interested in proving that the vector boundary is algebraic under the assumption that this curvature satisfies some pointwise growth when you approach the xi. And then Karen Uhlenbeck was in the setting of Mills connections, and then Harris and Tonegawa more in the spirit of Bando that I mentioned before. Now, what you will see next, well, what you will see is the main techniques in the proof, what I want to share with you. But first, let me tell you to a small detour for those of you who are not used with this sort of things, just to try to explain a little bit why integrability of the curvature has something to do with extension of the boundary. So let's first have a small detour to the rank 1 case. So let's say that we have a line bundle over the pointed ball in C2. So it's the simplest case that you can imagine. And then, now, in this case of rank 1, the curvature is simply a 1-1 form. So we have like a theta, the curvature form on the pointed ball. Now it has the good taste of being closed. So has this property. And then moreover, we know that is L2, right? This theta. Now, what we do is to have this form acting on forms with complementary degrees. So especially, let's consider a smooth 1 form with compact support on B. So here, remark that is B and not B star. So the support is inside B. And then the claim is that this integral is 0. Okay, so in the compact setting, if there is no star here, this is simply the theorem of Stokes. Now, the claim is that we can still do the same thing despite of the non-compactness, okay? And of course, as I guess most of you understood, what we will do is simply to use an approximation. That is to say, we take a sequence of cutoff functions converging to the identity here on the B star. And then what we can do is to write, first of all, that the integral we're interested in is this limit, right? Because it's absolutely convergent. And then since theta is closed, and then the support of this guy, rho k, is outside the star here, outside the origin in the ball, then you can integrate by parts. So now you have this limit to evaluate. Of course, by Cauchy-Schwarz, so with the test function, we have no quarrel, right? It's smooth, so the norm is uniformly bounded. So what we have to bound is this, the L2 norm of theta, which we know that is bounded, and then the gradient of the truncation functions. And then what is happening is that because psi here is just at the point, right? But this sequence here converges to 0. Okay, so the integral we want to evaluate actually is 0. So we have proved our claim. So now what's the upshot here? The upshot is that this form theta, well, this induces a current on the ball, which moreover is closed, right? So like I said, we have theta acting on forms of complementary degree, which is against 1, 1, because here it's C2. But then when you have theta acting on the differential of some one form, then this is 0. So this is what it means that it's closed. So theta is like a generalized version of a closed 1, 1 form on B. And then the dbar lemma still holds in the setting of currents, so we can still write theta as the Hessian of some distribution. But then theta is smooth outside the origin, so is f, right? So what we gain with this is that we can write our theta as the Hessian of some function which is smooth outside the origin. But then now if we twist the metric, the original metric with this exponential minus f, what you see is that the curvature of this metric is identically 0. So it's a Hermitian flat on B star, and Hermitian flat boundas on B star, they extend just like that because B star is simply connected. Okay. So that's the situation in the case of rank 1. So you see here the integrability of the curvature plays a crucial role. It allows us to say that this object is closed. Okay. Well, maybe one more comment here is that this is true in a much more general setting. It's enough to remove hypersurface in codimension 1, and then to have this one in L1, not L2 here, but like I said, I make it as friendly as possible. Fine, and then a second detour I would like to take is to consider the so-called, the simplest type of singularities. So that is to say, let's look at the submanifold, the analytic space in C3, sorry, given by this equation. Of course, we have a crossing, right? We have a singular point at the origin. So let's take the x0 is the regular part of this, right? So we remove the singularity, and then we take a Hermitian line bundle over the x0 here. And then now for the metric, let's simply declare that I want my geometry to be measured with respect to the Euclidean metric on C3 restricted to this x0, which now by miracle becomes a manifold, right? Because we remove the singularity. So we assume that, and we also assume that the curvature is L2. Then the main question may at least make sense, right? So, but we have to adapt it a little bit. So this this A2 singularity has a uniformization, right? In particular, is a quotient singularity. So now what I want is not to say that E extends, that E is locally free, but take the pullback on the uniformization. The question is, does this object extends? And then the answer is surprisingly, well, you see why surprisingly, yes, it does. And then why is that? So X is, of course, C2 modulo plus and minus identity. And then the map that embeds, if you want, X in C3 is given by this, U square, UV, and V square. So via the uniformization of X, the inverse image of the metric we consider is this one. Okay, so it's the Hessian of U to the fourth plus UV squared plus V to the fourth, absolute values. Now, this is not a metric, right? It has a 0 at the origin. Other than that, is civilized, but, well, it's a singular metric, right? And then the hypothesis that we have here, so translates into the fact that the pullback of this object on the unit ball in C2, well, it's L2, but with respect to this metric, not with respect to the Euclidean one. But then what is happening is something very strange, which only holds for A2 singularities, is that when you measure this 1-1 form with respect to the Euclidean metric in C2, and then you multiply with the volume element, it's bounded up to some uniform constant, numerical constant element, of the same thing, but with respect to the singular metric. Okay, see, so like I said, this is very special to A2, basically because the eigenvalues, so this one it is singular, but the eigenvalues are somehow proportional, right? So it degenerates in the same way. This is why we were able to prove this inequality, right? Because if you just look here, right, so you have this inverse image of G, you measure 1-1 form, so you have to divide with the eigenvalue. So this one would goes in the right direction, right, because it goes to infinity. But then you multiply with the volume element, which has the zeros. So it's not clear who will win. But then actually we have this inequality, and then we are back to the usual case. So like I said, the answer is yes, but for some reason which I don't understand, meaning that this inequality holds by explicit calculation, is not because of some conceptual reason. I hate to do that, but okay, that's how it is. So we derived the conclusion that the modulo, the pullback with respect to the uniformization, the inverse image of E extends. So even if, like I said, this argument is very specific to the A2 singularities, the question still holds. So let's assume now that we have X, which has Gaussian singularities. What's happening with this kind of question? I think it's a very interesting problem, but well, only partial results are known, and you will see soon why. Okay, now let's move forward after this small detour, and then let me try to explain to you a few ideas from the proof of the main result. So how come that we're able to solve this equation on X0 and get estimates? Now, Bando, if you look, he proceeds in 2 steps. The first one is to construct a solution of other type of equation, which is the Laplace, right? So the box is simply dbar star and the other one. And then and he's able to say that, okay, phi has this regularity. So it's in L2 and one derivative in L2. Okay, so this looks friendlier than simply d bar u equals to v, because you have some room to play. You have this other d bar star d bar, which is part of the picture. But then, so the second step is the reason why I decided to present this in this beautiful conference is that, as envisioned by Spencer, that is to say, generalizing the harmonic theory to the non-compact domains, Then the next step is to show that actually, since V is the dbar closed, then this part of the Laplace vanishes when we apply it to phi, and then we have so this equality reduces to dbar star of phi equals to V. So we found our U. Okay. So that's what I am going to explain to you next, how to perform these two steps. So let's start with some conventions. So first of all, even if I said at the beginning that X can be projective, what I would explain next is this case where X is given by the sublevel set of some strongly pluristochromatic exhaustion of the manifold M. One reason is that projective case is easier, and I hate these kind of things. So then now let's assume that Xi, let's fix locally some equations, and then accordingly we can construct a function which is smooth in the complement of our analytic set and which has this sort of degeneracy. So it has a logarithmic poles along Xi. Okay, so we can also normalize it by saying that the maximum is -1. And then why do we need this? Because it helps us to construct, helps us to construct a family of truncation functions, which has a very nice properties, as you will see in the next slides. So we can consider these truncation functions. So rho epsilon of the log of -phi. So it's here what you have is rho of log of minus log. Okay, so it's log like the Poincaré case. And then this rho epsilon, imagine that for a long time is 1 and then 0 at infinity. That is to say, it vanishes on a tiny small neighborhood of Xi. Okay, so it's then in this setting the epsilon tubular neighborhood will be simply phi smaller than the logarithm of epsilon, right? So just imagine you are like epsilon far from epsilon close to this Xi, right? It's like a ball, not exactly, but right. So so now the point is that instead of looking at x0, which simply consists in removing Xi, well, we will remove the whole epsilon neighborhood. So this x epsilon looks like an annulus, right? If you have in your mind the model of a ball inside the C2, so this one simply means that you remove a small ball of radius epsilon. And then the boundary has, of course, two components. And then somehow the idea is first to solve this equation, the box Laplace equation of phi epsilon equals to V on this set. Okay, so let's start modestly with trying to solve the annulus. Now, as you might know, for this type of equation, one always, not always, but one method is to use duality. So this relies on establishing certain a priori inequalities. Now, again, since if you look at the situation for a ball minus a smaller, one boundary is very nice, namely the exterior one, because right, it is given by the psi smaller than 1, and psi is strongly pluristochromatic. But then the interior boundary is problematic, right, because it has the opposite sign. And then so the type of objects we'll consider will be like this. So let's say that alpha will be a 0-1 form with values in E, and which vanishes on the boundary of this epsilon neighborhood of Xi. And then let's assume, moreover, that at the boundary of X, that is to say on psi equals to 1, we have this condition. So this condition means that that alpha is vanishing on the normal direction to the boundary. So again, alpha, I want it to vanish at every point on the small boundary, so to speak, and I impose only vanishing of the normal direction for the boundary of X, which is the right thing to do, because then alpha is in the domain of the dbar star. And now for some k, which is to be fixed later, let's twist the metric of E with exponential minus k times psi. So this corresponds to multiplying E with a very positive vector boundary, right? Ample, I'm sorry, here. And then, so now, in order to get this a priori inequality I was mentioning, what is known is that one is using the so-called Bogner formula as perfection defined by Kodaira, and together with Cohn-Mori trick to get rid of the boundary terms. This is where those conditions are appearing. And then you'll be able you'll see that actually this quantity, the dbar alpha and dbar star alpha square. So what we have on the right-hand side is something which is positive, which is the gradient of alpha, full gradient of alpha square, and then k times norm of alpha itself, because that's the reason why we multiplied with this k to gain this term here. But then in the Bogner formula, there is always the curvature term, and in our case looks very unfriendly, right? Because it's simply the norm of this tensor times the norm of alpha square with the minus sign. Here, C is a constant which depends on the curvature of the ambient manifold on X. More precisely, depends on the Ricci curvature on the trace. Wonderful. So here, what is our objective? We will be happy if we are able to show that this right-hand side dominates some small multiple of the norm of alpha, because then the situation is standard. But then here, what we have is this term, which is really bothering. So how can we get rid of him? Now, we will consider a cutoff function near which equals 1 near the loss I removed, xi, and then which has support in X. And then if you wave your hand a little bit, then you will understand that it is enough to absorb this quantity, like not only alpha, but xi times alpha. Okay, because basically 1 minus xi will be 0 near 1 minus chi, I'm sorry, will be 0 near xi. And then there is no problem. K maybe can be taken large enough to absorb that term. But the problem is what we do near xi. And then now here, what's the situation is that I want to take advantage of what we have, is namely that the curvature is in Ln. So by Helder, this is smaller than some constant, which I will write in a moment, times this norm of chi times alpha, right? So the constant in question is exactly this, right? The 1 over nth power of this integral. And then here, what we see is something which is very unpleasant, in the sense that here I have only L2 norm, but 2n divided by n minus 1 has the bad taste of being bigger than 2. So then here, well, it's minus something, which in principle has so we measure the chi times alpha with respect to a bigger norm in L, 2n divided by n minus 1. So the question is now, even if we can assume that this term is small, right? Because by shrinking the support of chi, this integral can be made as small as we need. But then still we have this chi times alpha to a norm which is bigger than 2, strictly bigger than 2. And so the trick now is what to do to bound this quantity here. And then the trick is to use the Sobolev inequality, which is a very important result, stating that, well, in our setting is like this. So for any function, the L2 over n, 2n divided by n minus 1 norm square is smaller than this quantity, the norm of f in L2 plus the L2 norm of the gradient of f. Okay, so here you have a norm which is the one we're interested in, right? And then L2 is good, if you remember the previous slide. And then we have an additional term, which is the gradient of f. So now in our case, the function f, which we take here, is simply the chi times the norm of alpha, the norm of our test form. And then the observation is that the gradient of this f is smaller than the gradient of the product of alpha and chi. And then again, by if you look long enough at the previous inequality, you will see that in fact, thanks to this here, this term, which is the positive in Bochner formula, will dominate the curvature term. Okay, so this is where somehow why I got so enthusiastic about this result of Bando, this proof of Bando, because in the L2 theory, one rarely is using this gradient term in Bochner formula. One is simply happy with the fact that this is semi-positive, so okay, forget it. And then we look at the leftover. But then here it's crucial in order to absorb the curvature term. Fine, so then all in all, we will get our a priori inequality as here. So this will hold for all forms alpha as above. And then, as I already mentioned, I want to solve my equation by using duality, and then the Hilbert space that we will use is simply the closure of the space of such forms with respect to this norm. So this gives exactly this condition that I wrote here. And yes? Sorry. And then on this edge, the scalar product will be given by simply taking the dbar of each one of them, take the bracket, and then the dbar star. Okay, this is indeed positively, well defined because of this inequality here. And then the usual theory now, when you have this handsome inequality here, shows that you can indeed solve the equation. So we can find some function phi epsilon in H, in our Hilbert space, such that it satisfies this equality in weak sense, and for which we know a priori that this norm here is smaller than some constant times V. Okay, so you have a lot of epsilons all over, but there is some fixed quantity, which is this one, right? So the constant C is independent of epsilon, and so is this norm here. Wonderful. Now, the point is that this phi epsilon, thanks to the usual elliptic theories, right? So here you are really in the very, very standard setting of a problem which has a Dirichlet boundary condition here and Neumann boundary condition for the boundary of X. So this one is smooth. But in general, it's not true that the second part of the Laplace, namely this one, is zero. Okay, so and it's not only our fault. There are domains on which this is simply wrong, right? You cannot solve the equation on annulus. And then the way out is to show that even if this is not true for some epsilon fixed, the hope is that this will hold when we take the limit. Okay, so that's what we will do next, show that this holds here. And of course, when we talk about limits, we need to study some uniformity properties of this sequence, because if not, we cannot take any limit. So then the first thing to remark is that when you restrict to some compact inside X, then this family of solution is uniformly bounded in whatever norm you want, again, by the standard elliptic theorem. Then now let's look at this situation. Consider any cutoff function with support in X, which is 1 near the loci we took out, psi. And then in the, well, you will not actually see this in action, but you have to take my word for it. So this quantity is something we are interested in to evaluate the Laplace of phi epsilon time multiplied with some power of the norm of phi epsilon. And then what we want to do is to integrate by parts. And then actually what is happening is that the usual integration by parts formula holds. Now, usually, so when you write this kind of formulas, there is of course a boundary term. And then here we have two boundaries, right? The small one, the boundary of the ball of radius epsilon, and then the boundary of x. Now the boundary of x is out because of this theta, and the boundary of the small one, so to speak, is vanishing because of the condition we impose to phi. Okay, so all in all, we have the same way of integrating here as in the compact case, if you want. And then now, as you know, the slogan, when you want to estimate some function, take the Laplace. That's exactly what we do here. So we evaluate the Laplace. The Laplace here is the one of the analyst, that is to say the trace of IDD bar. And then with respect to this metric G here. So it so happened that, so now let's look, what are the terms to expect? Well, there is, I measured this with respect to two objects. I need a metric on E, which disappeared, so it's the vector bundle, and then a metric on X. So when you take this, we take advantage of the fact that Laplace of this phi epsilon is V, so this will give this contribution here, which is fixed. And then some terms which depends linearly on the curvature of E. Okay, that's what we get. It's a very precise formula. So this function, it's independent on epsilon, but of course the coefficients of the curvature, they get worse and worse as epsilon goes to 0. And then a version of it is here. Actually, f theta and constants, they are not the same, but the main thing is that they are independent of epsilon. So actually the dbar of phi epsilon square is bounded by this quantity. Some universal constant plus this linear operator of the coefficients of E, of the curvature of E, times the square, and then Laplace of it. Okay, so we will see what role are playing these inequalities in a second, but then a consequence of the first one is the following. Namely that there are some universal constants here such that the LQ norm of this phi epsilon is bounded uniformly with respect to epsilon. The price to pay is pretty small, that is to say it's enough to shrink the domain a little bit. For each Q you have to shrink it more and more, but then if you're happy with a fixed Q, then we are good. So this is one of the important ingredients in the story, and the proof is the first inequality here, which you apply repeatedly. That is to say, use a Moser iteration process in order to derive this sort of inequalities. Okay, so the same thing. That is to say, you multiply here with absolute value to some power, and then here you integrate by parts. This is why this formula comes into the picture. And then you solve Sobolev inequality, and then you upgrade the integrability of phi by this procedure. Wonderful. Now, the trouble. What is the trouble? The trouble comes from the fact that we cannot invoke a similar argument. That is to say, to derive the fact that the same holds for the dbar of this. Simply because a priori it doesn't vanish on the boundary. That's exactly the problem, if you want here. The anti-holomorphic derivative of phi epsilon. So I mean, intuitively, why we don't expect this one to vanish on the boundary is like when you have a domain. Let's say, forget about everything else. We have a domain, and we look at the Laplace equation delta of some phi equals to another function. and then phi is 0 on the boundary. You cannot add one additional requirement that the Laplace, that the derivative of the solution, you want the derivative of the solution also to vanish on the boundary. Of course, you can't do that because you have uniqueness, okay? That's exactly what is happening here. So this norm, in general, it will not be 0 on the boundary of the small, on the small boundary, so to speak. And then, so why it vanishes at the limit? Let's see now here. First of all, the first observation is that this one is an equality between smooth objects, so we have absolutely no shame of taking one more dbar here. Dbar of v is 0, and then when you apply dbar to this operator, that's what you get, right? Now, what we will do is to consider two parameters, epsilon and eta. And then what will happen is that if epsilon is much smaller than this other one, well, you can integrate this quantity here against rho eta is the truncation function I was mentioning at the beginning with the Poincaré type, if you want. Now, this rho eta is 0 on the boundary of the ball of radius epsilon, and then so we can write this integral here, right? Integral over the whole x. And again, since now here we really use the fact that near the boundary of x, this one is in the domain of the dbar star. This means that the normal derivative of this form also vanish at each boundary point. So this is why we can integrate by parts and infer that, so we can move this one here. Again, the boundary, there's no boundary term because of this and because of the choice of eta. So we have this. We are on the right track. If we can move this truncation function out of the dbar star, then we are really happy. And then that's exactly what we do. So if you expand this term here, and then use Cauchy-Schwarz inequality, then what you see is that the integral you are interested in is smaller than this one. So the norm of the cutoff function times the dbar of phi epsilon. So now you see why I was so eager to tell you that we don't know about LP integrability of this one beyond 2, simply because I would have been happy here to conclude that, well, I can get rid of this because it's in LP, and then with this dbar of rho eta we negotiate. But then that's not the case. And then, but what we can do is simply to remark that, in fact, now we use the second differential inequality, and this dbar of phi epsilon, the norm of this one is bounded by this, right? So it's this one is the same, and then what we see is a constant times the unfriendly curvature times phi epsilon squared times the Laplace of this guy. Okay, so this is our new enemy here. And then, yeah, so this is the consequence of the second differential inequality I was mentioning before. And then, unfortunately, this is where we have to use the codimension of psi is at least 3, because this increases dramatically the integrability property of this gradient here. So basically, if you look how to handle this term, so for the constant, it is enough to have dbar square tending to 0. For this one, if you look, if you apply again the fact that the curvature is in Ln, and then you will see that it's enough to have this one in L4. But then the bad one is this one. So we can move the Laplace. We can integrate by part, and this one have it equal to phi epsilon squared times the Laplace of the dbar eta square. But then the problem is that this one is in LQ now, so I can raise it to arbitrary high power. But then I still have to deal with the Laplace, the norm of the Laplace of this. And then if you look into his eyes, you see that codimension 3 is exactly the right condition for this norm to go to 0. Okay, so that's precisely the situation here. So in conclusion, the integrability properties of these cutoff functions that we need basically force the analytic set to have at least codimension 3, and then under these circumstances we can get rid of so when you take the limit in the right order, because we have the hierarchy between the two parameters. But anyway, so we can bound this uniformly with respect to epsilon and then take the limit with respect to eta. So this will converge to 0, and then this will show that I hope I wrote, yeah. This will show that the dbar star, dbar phi equals to 0. Okay, so indeed, we can get rid of this, but not for a fixed epsilon, but at the limit. All right, so in conclusion, so we solved our equation here, because we simply take u as the dbar star of phi, and on the top of it we have a handsome estimate for the norm of the u square, as I mentioned in the paper, yeah, at the beginning. So again, my somehow enthusiasm for this is simply to see that there is one somehow possibility to get out of the usual L2 to apply the L2 theory, even if the curvature doesn't have a sign, provided that you have this integrability condition satisfied. All right, now I will mention a few results about singular analytic spaces. Unfortunately, it's not yet clear to us how far we can go in this direction, but anyway, let me just tell you what we have for now, my collaborator and myself. So we have here a compact normal space X, and then we have to decide what is a Keller form on such an object, and then in general we agree that what we want is this 1-1 form to be Keller when you restrict it to the regular part, but not only that, you want it to be compatible with the local embeddings. That is to say, locally X sits inside some Euclidean space, and then you want to say that omega is the restriction of a Keller form on Cn. Okay, so this locally comes from the ambient space. Now, the bad news is that even if this metric looks very natural, there is an important differential geometric invariant which is simply not bounded, and this is the Ricci curvature already. Okay, so the Ricci curvature, if you compute in the very, very simple situations, for this, it simply blows up. And then this is a very bad news given the method that I was trying to explain to you a few seconds ago, because the geometry of the manifold came into the picture several times. There was some constant there, which was written as C of X and G, and then that was involving curvature of the manifold. And then, yeah, even if we stay away from the singular loci, fatally the unboundedness of this will create troubles. Now, a very nice class of singularities, which plays an important role in the minimal model programs, is that spaces with Kawamata terminal singularities. And then I will not tell you what, I will not give a formal definition, but let's see what are the properties that these spaces have. In the first place, we do have a canonical. Some power of this is locally free. And then now that's a theorem, is that outside a set of codimension 3, we only have at worst quotient singularities, right? So they are rather friendly, but not quite. You don't know what's happening in this Z, but okay. And then also when there is a, so to speak, competitor to this picture here, is that on any space with log terminal singularities, we can construct, there is a metric, let's say omega orb. We simply have orbifold singularities at every point here in the complement, right? So that is to say, via the local uniformization, this omega orb is quasi, so looks like the Euclidean metric. So if you want, this metric is also bigger, strictly positive, like bigger than some multiple of Keller metric in this sense. And then what is even more nice, what is even nicer is that the Ricci curvature is bounded, two-sided actually. And then, for example, let's look again at this A2. So the omega that we got, as I explained a few seconds ago, this one looks like that, right? Like the Hessian of this expression. But, and then the omega orb, it looks much nicer, right? Is quasi-isometric to the Euclidean metric. And then so what also it's nice here is that the Monge-Ampère theory on those spaces, although singular, it's well understood, partly thanks to recent progress. And then this metric here that we have actually is not explicit at all, but obtained as a solution of a Monge-Ampère equation. Okay, so it has nice properties, but it's somehow difficult to handle. It's not like we write some equations and that's it. I mean, it's not like we construct it by hand. It's obtained as the solution of a Monge-Ampère equation, and that one we don't know what's happening near the singularities. Okay, which are not quotient. The quotient singularities looks like it's as nice as possible. That is to say, precisely like that. Okay, so this is part of the definition. These two are two important results in the theorem. And then, a last thing I would like to mention is the following: is that let's take a vector bundle on the regular part of this such a space with log terminal singularities, and then assume that on the regular part, this one is the L2 norm of the curvature is finite. But then here, the important thing is that we measure it with respect to this orbifold metric, not with respect to the, let's say, smooth metric, the one coming from the ambient space locally. And then if this is convergent, then this E extends as a reflexive sheaf on the whole space. And then if moreover, instead of 2 here, we have N, then the restriction to minus Z defines a Q vector bundle. That is to say, when we pull back E with respect to the local uniformizations of X, it becomes an honest vector bundle. Okay, so just one word about the proof. It's the arguments above. Again, here we take advantage of the fact that we control the Ricci curvature of this one. And combined with a very important result due to CU, namely the slicing theorem. Right, it's important, for example, here on a generic slice, the curvature will be still L2, and then we can extend it, and then this is where Yumtong's result comes into the picture. Okay, so I will finish a bit earlier than I should, but I'm sure you will not mind. So thank you very much for the invitation again. So I'm done. Thank you.